Okay, good afternoon, everyone. Let's go to our second chapter. This is dislocations and strengthening mechanisms 2. And this would be the chapter 5 in the Read Here's physical metallurgy principles. And also I will add some of the contents from uh, Callister's material science and engineering from the chapter 4 and 7. And please visit the Moodle platforms so that you can download the PowerPoint slide and to watch the pre-recorded video. And if you have any questions, just feel free to email me anytime if you have questions. Okay, so as usual, let's first talk about why we need to study this chapter. This chapter is about dislocation and its strengthening mechanisms. And also we have an important start, that is scientists find out the result that the plastic deformation amount in soft specimens is many times greater than that in a hard worked specimens with dislocations. And it's very important to know that for the sample with hard worked conditions such as cold rolling or hard rolling, it will cause a lot of dislocations in the structure. And for the soft specimen, it means that the hard worked specimen has been annealed in a furnace, and length, it will experience annealing phenomena. We will talk about it in the next few chapters. So with the annealed specimens, the dislocation density will decrease, and the results will find out that the plastic um, deformation amount. This is similar to the concept of ductility. So the elongation or ductility of soft specimen is many times greater than that in hard worked specimens. And this is related to the dislocation density. Okay, so we know that dislocation can affect the material's property, especially for the mechanical properties. And during the process of plastic deformations, dislocations must be created during the process. So first, let's imagine during the plastic deformations, we know that it must be the shear stress or shear force that can cause the dislocation motions, as we learned about in the previous chapter. So first, we will have external stress, and this would be the shear stress. And this shear stress will cause dislocation motion. And now we have a very important questions. What is the dislocation coming from? Are these dislocations the original one, or are these dislocations the newly formed ones? Okay, so we have two types of dislocations considering the status, the original one or the newly formed one. And length, when dislocations move during external force, it will produce shear strength. So we will have this plastic deformation amount. And what we said here, dislocations must be created during plastic deformations. The reason for this is the plastic deformation amount in metals is very large. However, if we have the original dislocations only for the shear strengths, it will not be able to produce such a large strength value. So we can conclude that there must be newly formed dislocation during the plastic deformations. And for you, you can see here, this picture is the TEM image showing a lot of dislocations. And then let's talk about a very important mechanisms. This is what we call Frank Reed source, Frank Reed source for dislocation generation. So when you see this term, it is about dislocation generation. It is a mechanism. So what is Frank Reed source? When two edge dislocations intersect another edge dislocations, then it will cause a phenomenon. We will talk about it here. Intersect is what we learned about in chapter 1, right? So first, let's see here. We have two edge dislocation lines intersect edge dislocation x, y. So we have three edge dislocation here. And this one and this one, the dislocation lines are normal to the slip plane. So the gray area here, this is slip plane A, B, C, D. And for this X, Y edge dislocations, it is on the slip planes. And based on what we learned in chapter 1, dislocation can only move on the slip plane through the slip, right? And the other mechanism is climb. So for XY edge dislocation, it can move on these slip planes. If you have a shear stress with these directions, so it will move to left or right, right? This is a parallel relationship. So here you can see the note 1. The edge dislocation motion is parallel to the shear direction, and it must be on the slip plane. However, for these two, edge dislocation 1 and 2, because they are normal to the slip planes, so they cannot move during this shear stress. Okay, so based on the introduction here, we can know that these two cannot move on the slip plane, but XY can move. However, for the point X and point Y, they are the intersections between these edge dislocation. So X and Y must be fixed because edge dislocation 1 and 2 cannot move. This one and this one cannot move. However, XY should be able to move. So XY will fix, but the middle one can move. So you can see here. First, we have XY, this is this XY. SY is on the slip plane. And then when we have a shear direction here, this dislocation line will move to left. However, X and Y must be fixed. So it will move like this, like A. So first, this is the first stage, line XY. The second stage is A. So you can see it move, and then B, and then C. And because XY are fixed, So eventually you will see the results like this one. It will go like this structure. So we can form this C curve with one intersection. We call it M. And M is an intersection. An intersection like this one, it will cause cancellations of dislocations. So it will separate into two. The one is the dislocation loop, and the other is this one. Okay, so this is the first part, and the second part is this loop. All right, and then you will see that it formed a D for the dislocation loop, and then this step will continue to go left because we still have the shear stress. So after we go from step 1 to step 5, you see that line xy go to D plus line xy, and D is the dislocation loop. So you can see that we have a dislocation intersection like this one, and eventually it will continuously produce new dislocation loop. So this is the Frank rate source for dislocation generation. It will produce dislocation loop. But first, we must have this dislocation intersection, and then it will produce more dislocation loops. And then we now know the first type to form dislocation, that is the Frank resource mechanisms. We can also have the second type for dislocation generations. We call it dislocation nucleations. And for the nucleation of dislocations, we can further classify them into two types. One we call homogeneous, the other we call heterogeneous. For homogeneous nucleations, it means that the dislocation will be formed in a perfect crystal. So it will come out from nowhere, right? There is no defect in a perfect crystal. But actually, it's not likely, okay? Not likely for this one. And the second one is heterogeneous. So we must first have impurities, and then dislocations will form based on this or next to this impurity. So this is what we call heterogeneous nucleations. And the note here, you can see the defect, for example, like a surface or impurities. Both of these two are defects. It will make it easy for dislocation generation because homogeneous nucleation is very, very hard, and heterogeneous will be easy. And let's see the observation of dislocations. How to see the dislocation nucleations. And we have one very simple method to observe it in crystal. That is, we used etching reagent. And then we use the agents so that we can etch the specimen. However, we know that dislocation are defects, and defects are easily etched. So for example, this is a grain A, this may be grain B, this is the grain boundary or dislocations. And then the dislocation, because they are defects. So when you use etching process, these regions with dislocations, it will be etched with a higher rate. Okay, and also we can see here, this is a small pit. We call it etch pits or etching pits. This is a large pit, so it will be formed as a newly nucleated dislocations. And these ones, it could be known as the dislocations with low angle grain boundary. So dislocations or low angle grain boundary, they are the similar concept. And we will talk about this in the next few chapters. And in general, we will use this kind of the material, lithium fluoride crystals. The researchers usually use these crystals to do the studies for the dislocation generation. And then let's first review for this page. We have learned it in the first chapter. So when plastic deformation occurs, we apply stress to the material, right? So there are energies. And with these energies, it will be used for deformations. However, this deformation energy, some of them will be stored in the lattice, stored in the interior. We call it lattice strain energies or the stored energy. Okay, and the rest of them will be dissipated as heat. And you see here, now we have edge dislocations. This is positive edge. So we will have different parts. The regions above dislocation lines we see here, this is extra half planes. So it will be the atoms will look like squeezed together, so it will be compressive. And then here, this is the tensile, and near dislocation line we have shear. However, for screw dislocations, we first have a dislocation line and a lattice distortion, experience lattice distortion around this dislocation line. So it's the pure shear. And we also know that when the distance away from this region, for example, these locations with distance r, if r increased, the strain energy, the energy will decrease. Okay, this is the statement here. Okay, let's talk about dislocations interactions. We will have repulsion and attractions. So for repulsions, let's take edge dislocations for example. If we have two edge dislocations and they have the same sign, for example, the two positive edge or two negative edge. So the same sign, for example, like here, we know that for a positive, we will have compression and tensile, right? But we have two edge dislocation with the same sign. So here we have compressive stress field, and they will experience repulsions. Okay, so this is the first one, repulsions. And this is one very important reason for strain hardening. And then we can also have attractions. So if we have positive edge here, compression and tensions, and negative edge here, compression and tensions. So compression and tensions, these two stress fields will attract each other. So that's positive edge and negative edge, they will combine together. Eventually, we will experience dislocation and annihilations. In other words, dislocations will disappear after they meet each other. So it will form perfect crystals. Okay, and actually this is the concept for recovery. Okay, let's talk about band gliding. Band gliding is actually a deformation method, and this method is due to the result of the slip. So, for examples, we have a stick, a material like this, and then we applied a torque or a bending moment to it, like this one. We have an M here, and then it will experience physical bending. And what is the mechanism for this physical bending? Because for plastic deformations, we know that slip or climb will occur. And how about these bendings? So first, we have the materials with this external stress. And now let's analyze the stress distributions. So we can see that we can draw this structure. And for this region from A to A here, this region experience compressive stress. For this region, it experience tensile stress. In the middle one, there will be net zero stress. So with a different distance away from these two ends, they will have different stress values. And we can use this equation to express the stress with different distance. Okay, but you don't need to memorize it. First, you now just need to know that the bending is about the slip. And now let's talk about how slip will occur in this structure. So let's talk about the deformation mechanism. And first, we know that we can draw the stress distribution here. And then we know the material like this one, right? So, and we now know that we can draw this as compressive and tensile stress. However, for slip must occur on slip planes, and also for dislocation motion, it must be shear. So we need to draw the shear component from this one, and then it must be on the slip planes. So let's first assume we have a slip plane here. Okay, this is the slip plane, and then the compressive stress and tensile stress must be resolved for the shear component. So first, this would be the compressive stress, right? This is the tensile stress. And we must calculate the shear component. So eventually, it will look like this one. So this will be the shear component on the slip plane. And then the band gliding mechanisms, as we mentioned, is related to the slip. And however, as we said, it's not possible for the original dislocations to cause the large plastic deformation amount. So we must have a mechanism for dislocation generation. And here is the Frank Reed source mechanism. As we said, the original one are not enough to cause this plastic deformation. So we now have a slip plane and a shear component like this. And then let's now talk about it in more detail. So let's first try to consider positive edge and negative edge, because this is the slip line, right? So we have positive edge and negative edge, positive edge, and negative edge with different shear stress directions. And first, let's see this one. With this shear stress direction from right to left and the positive edge, then this dislocation will go to here, right? So let's talk about it one by one. For this one, this is positive edge. It will go to here. This is the surface. So when you go to the surface, it will be gone, diminished. How about this one? Positive edge, go to surface. And this one, negative edge, it will go to the center. Negative edge, go to the center. And then it will experience accumulations. Okay, so they will be accumulated near the center. This is because all of these dislocation lines are with the same sign, and then when a lot of dislocation with same signs together, they will experience the repulsive stress. So they will accumulate it in the middle. They will not combine together, right? And then let's see the statement here. So this negative edge will accumulate it near the centers, and then the compressive and tensile stress magnitude are getting smaller near the center. So first, let's see the statement here. We now know that for the positive one, they will go to the surface. However, for the negative one, we know the stress distribution, right? It means that the outermost region with larger stress directions, and it will with larger stress direction. So when you go to the center will experience net zero stress. So when it goes in, the magnitude of the stress will get smaller. Eventually, they will accumulate near the centers. And then, how about left hand and right hand screw on this slip plate? Because for the screw dislocation, the motion is perpendicular to the stress directions. So on this slip plate, it will move to the backward or frontward on the slip plate. So it will be into this screen or out of this screen. But eventually, they will also disappear. They will also move to surface. But the surface is different from the positive edge. And this is what we said. Why this edge dislocation will accumulate near the region, near the center, because dislocation with the same sign will experience repulsive force. So based on the result here, you will see that all of it are negative edge dislocations. Okay, and then let's talk about rotation slip. So first, the important one is we have three types of deformation. The first, simple shear. Okay, for example, simple shear. Right? This is simple shear. And then band gliding, as we said in previous slide. And the rotation slip. We are going to talk about this in this page. And this is about first, we have a crystal. Originally, we have A, B, C, D. They should be on the same line. But after the rotations, it will separate to two different lines. And this will be on the slip plane. So a single crystal can rotate plastically on a slip plane. And this slip plane must have numerous slip directions so that it can form this kind of rotation slip. So for example, like FCC 111 or HCP 0001 planes will be the ideal cases for the rotation slip. And you can see here, this is about the rotation slip. We have two conditions. This is the single array of screw dislocations. This is the double array of screw dislocation. And actually, if you look closer to these two pictures, you will know that it involves complex deformation, and also it will involve more than one set of screw dislocation. So I think I just leave the slides here, but this is just supplementary information for you. Okay, and let's move on to talk about the slip system. Slip systems contains slip plane and the slip direction. But first, let's talk about the concept of slip system. And dislocations do not move with the same degree of ease on all crystallography planes. It indicates that dislocation will have a preferred plane and preferred direction for slip. Okay, so that's the concept for slip plane and slip directions, which are the preferred plane for slip and the preferred direction for slip. And we also know that the slip directions must be on the slip plane. And for the combination of slip plane and slip directions, we call it slip systems. And it's very important to know that, as we said, the slip direction must be on the slip plane. So the slip direction and the normal direction of slip planes would have a perpendicular relationship. So we can use the mass, that is the inner product between these two, must be zero. Okay, so that's, you can see here, this is the inner product of these two vectors. And because we know that it has a 90 degree of angular difference, so cosine 90 degree equals to 0. So you can check it to check the inner product between these two vectors. It must be 0. If this is not equal to 0, then this is not the slip direction and slip plane. And also, as we said, dislocations will have a preferred plane and direction for slip. So these slip systems, of course, depends on the crystal structure. For different structure, they will have different slip systems. And during the plastic deformation, this is the slip for dislocation motion, right? So the motions of dislocations must cause a minimum atomic distortion for slip, and minimum distortions reveals the stable status. So we can conclude that the preferred plane for slip, that is the slip plane, will be the highest planar density plane for the crystal structure. And the slip directions would be the highest linear density one for the slip direction. Okay, and we can also use the following illustration to let you know about the slip plane and slip directions, about the shear strength and the energy aspect. So first, you can see a plane here, and we choose two different slip directions. So first, you can see the direction of MN directions, and also the other one is QR direction. You can see here, MN is the the highest linear density one. However, for QR is not. And if we try to have a shear along MN direction, you can see here, we choose it for 1 atomic distance here. Okay. And however, for the shear along QR direction, this is not the close packed directions. So the atoms go from here to here, right? So you can see that we see the comparison here. For the atomic displacement from this atom to here, we have 2r, okay? However, here it's larger than, for A conditions, is 2r. For C, is larger than 2r, okay? So for the atomic displacement, C is larger than A. And of course, for the Burgers vector is about the magnitude of the stress and also the direction of stress. So if the magnitude of the stress is higher for C than A, then it will be C larger than A. And then the strength energy produced, because it has a larger displacement, so C will be larger than A. To sum, we can know that A will be stable for the slip process. So the fact here is the lattice arrangement will affect the slip. And after the dislocation passing through perfect crystals, this is the rule. It must be unchanged. Okay, I should mention this earlier. And the shear strength produced must be as small as possible. So based on this result, we will know that A will occur, not C. Okay, so we will see this condition, not this one. And this one is the close packed direction. And also, here is a fact that one slip plane can have more than one slip directions. And we will call this all slip directions as equivalent. So you can see here, this is the close packed plane. And for FCC 111, we have a close packed plane. For HCP 0001, we also have a close packed plane. And here we can draw 3 different directions. So one slip plane, this one, and this one, can have more than one slip direction. For example, we have 3 here. And all of these 3 directions are equivalent. And let's talk about some fundamental understanding of crystallography. So for some crystal structures, of course, not all of them, it will have several non-parallel directions with different indices, but they are crystallographically equivalent, as we said here. So, for example, in cubic system, 100 and minus 100 and 010 and so on, they are equivalent. So we will call them as a 100 family, okay, family of directions. However, for some crystal structure, and the same may not, the same indices, the same example may not be true for the other crystal systems. For example, 100 and 010 are equivalent. However, 100 and 010 are not. Sorry. This one is equivalent for tetragonal. But here you can see this one and this one. They are equivalent for cubic, but they are not equivalent for cubic because one stands for the A unit length for the crystal structure. C stands for the C unit length of the structure. And for cubic, A equals to B equals to C. So we can draw it as a family of planes. But for tetragonal, A equals to B not equals to C. So this one and this one cannot be considered as the same one. And also for the directional indices, a half one, 112, and 224 are actually the same, but we will write it as 112. Okay, and also we will have crystallographically equivalent for planes. For example, we call it this one 111 family of planes, and it contains of a lot of planes. And also this one, for example, 111 family of plane for cubic systems are not exactly the same as that for tetragonal systems. And you can see here, for tetragonal system, 100 family of planes contains these four, okay, these four planes, but not these two, because A equals to B not equals to C. Okay, and let's first talk about some math rules. We will use it later. And here, let's try to imagine we have a material and we apply a tensile stress here. This is a tensile stress to this material. And we know that the slip must be on the slip plane. And the slip plane will be in this structure, but we don't know it for which plane. So we first assume that this one is the slip plane. Slip planes has angular difference for this cross-section with theta. And then we can try to calculate the shear stress here. This is tau, okay? As we said, this is the slip plane. So we must calculate the resolved shear stress on this plane. So this is the tau. And okay, sorry, this is tau prime. So we must calculate the tau prime. And this is how we processed. First, we have tensile stress F and A0. And here we must calculate F double prime and A0 prime. And for the A0 primes, we can use this equation. This is an area for ellipse. Okay, this is an ellipse. And this one is a circle. So this is a cylindrical structure. And then we must calculate F double prime here. and f double prime will equal to f sine theta. And then we can use these equations to calculate E equals to alpha sine theta and cosine theta. So this is how we calculate the shear stress, okay? Shear stress as a function of orientation. Orientation of plane, this is theta. Okay? And the previous slide is about the mass rule. So let's learn about how we use it in the slip in single crystal. As we said, we first have a F here. We have a F. Then we must calculate the resolved shear stress. And the purpose is, even though we used pure tensor to this specimen, this is a cylindrical specimen. However, we must have the shear component. Otherwise, there will be no slip. Okay, we must calculate the shear component on the slip plane. So this is what we call the resolved shear stress, and we use these equations. Actually, this is the same as we talked about in the previous page. We use the sigma sine theta cosine theta, right? And here we use different terms. We use phi and lambda, this one. So this is for the cosine phi. This is for the calculation of elliptical area transitions. Okay. And cosine lambda is for the resolved shear force. Okay, force on the slip directions. And you can also see the term here. It's very important that although you have the same cosine here, but try to find out that phi and lambda, they have different meaning. For phi here, it's the angular difference between the force and the normal to the slip planes. And for the lambda, it's the force and the slip direction. Okay. And how to obtain this phi and lambda? So we can use the mass rule. As we used previously, this is the inner product equations. Okay, inner product equations. And then we can get theta here. And theta equals to cosine minus 1 with this one. Okay. But if you try to calculate this, you must use the calculator. Okay, so for the slip in single crystal, now let's talk about an important concept we call critical resolved shear stress. We know that resolved shear stress is just the stress on the slip plane, right? This is the resolved shear stress from the external stress. So here, the shear stress on a certain plane, we use this equation, resolved shear stress equations. However, try to imagine if the shear stress is on a most favorable slip system. We know that we could have a lot of slip systems, and we will also go deeper in the next few slides. So we have a lot of slip systems, and we must have one most favorable one. So this one will cause a maximum stress because the higher the shear stress, it can be easier to cause the slip. So the maximum for this one will be the maximum for this combination. Okay, and sigma is fixed. Okay, and when tau r reach a critical value. This value we call critical resolved shear stress. Then slip can initiate. Try to imagine the stress strain curve. Stress strain curve. When the stress increased, the strain will increase. And initially it will be elastic deformation. And after it reaches a certain point, yielding will occur. So it will start to have the plastic deformation. In other words, this one, sigma, reach sigma y. So when yielding occurred, this stress, we call it critical resolved shear stress. And then because yielding occurred, then this yield stress, we call it yield, this stress, we will call it yield stress. And then this cosine phi and cosine lambda must be the maximum because we will only have one slip system to initiate, but it's just the first one. And after that, after you increase the stress, the other slip system will initiate too. So based on this equation, we do the rearrangement, we can get that this is the yield stress. Yield stress equals to tau CRSS cosine phi cosine lambda maxed. And when slip must occur, tau R must be larger than tau CRSS. Okay, this is actually a very important equation. And the maximum stress for yielding will be this one. However, it's very important. This is just a mathematical estimation because for phi equals to lambda equals to 45 degrees, this will not happen all the time because for the materials you apply, for example, tensile stress. However, you don't know about the slip plane and slip direction. So perhaps the angular difference will be 55 degree or maybe 23 degree. So it will not always be 45 degree. Okay, so this is just mathematical estimations. Okay, and for the resolved shear stress and critical resolved shear stress, we have some important concepts. That is the resolved shear stress. Okay, this is tau R. Is a function of stress and orientations. Okay, this is phi and lambda. We just use this equation. So you can see that if we try to induce slip, we can try to increase the stress, or if the orientation match, it may be easy to induce slip. And for this cosine phi cosine lambda, we have a name for it. This is called Schmidt factor. And Schmidt factor is higher. If this factor is higher, it means that if you used the same external stress, you will give a higher tau R, so it will be easy for slip. Okay, so Schmidt factor is about the orientations. To let you know that the orientation of your structure is easy for slip or not. And the maximum value would be 0.5 here. Okay, so you can see here, this is the tensile stress, and this is the cosine theta, cosine, okay? This is just a different expression. You can see that with different Schmidt factor, we will have different tensile stress here. And here, when Schmidt factor equals to 0.5, then 0.5 is the maximum one, right? So it will be easy for sleep. And this is the ear stress for fixed CRSS. Okay, so what do you mean for the ear stress here? This is the ear stress, we write it as the tensile stress. Ear stress for fixed CRS. Fixed CRS means the same material, right? The same material. And the ear stress with a lower ear stress, it means that it will be easy for sleep. With a higher ear stress, it will be hard for sleep. So with the highest, the maximum Shimmy factor 0.5 here, the lowest ear stress, it will be easy for sleep. Okay, you just need to understand these equations and also the definition of Shimmy factor. And also we learn about the critical resolved shear stress. It means that when the tau R increased and reach tau CRSS, length yielding will occur. And this one is actually depends on different materials because different materials with different crystal structure, it could have different sleep systems. And we will talk about it later in the next slide. And also for the yielding strength, okay, this is a material property, a mechanical property. It will depend on the critical resolved shear stress and orientation. But how to see that? This one. This one is the ear strength, and it depends on tau CRSS, and also this one depends on materials. And also this one depends on the orientations. For the same materials, we will have the same tau CRSS. But if we change the crystal orientation here, we can also change the sigma y here. Okay? And for more important concept, we can know that the critical resolved shear stress, tau CRSS, strongly affected by the composition and the pretreatment. For example, when grain size decreased, we will have grain boundary strengthening, and length, the material becomes stronger, so tau CRS will increase. And with the less impurity, it means that with the alloying process, we will have the solid solution strengthening, so CRS will increase. When the temperature decreased, temperature will affect the dislocation mobility. So when the temperature decreased, it will cause a low dislocation mobility. Low dislocation mobility means that dislocation is hindered, hard to move, so tau CRS will increase. And as last one, with a higher strain rate, tau CRS will increase, but also the ductility will decrease. Okay, this is a trade-off. And when the crystal possess several crystallographically equivalent sleep systems, for example, FCC have 12 sleep systems, and they will always be the first one to initiate. So sleep will first initiate for the one having the highest resolved shear stress or the lowest critical resolved shear stress. Okay. And now let's talk about dislocation density. Dislocation density, or rho, is an important because it's related to the mechanical property of metals. It's about the strengthening mechanisms. This one is strength hardening. We will talk about it later in this chapter. So for the descriptions, first, the dislocation can be expressed as length per volume, okay? Or it can be expressed as number per area. For example, if we choose the method 1. This is length per area. So we will first define an area, okay, and then calculate the length of all of these dislocations. Then we can get length per volume for the dislocation density. And the method 2 is number per area. So first, we must reorient the specimen to a specific directions so that we will not observe the dislocation lines like this one. We will observe it like a dot, okay, like a dot. For example, if we have edge dislocations with extra half plane, then where is the dislocation line? Here, right? So here we choose the right positions, then we can observe the dislocations in a dot, right? This is a dot, but we must first etch the specimens. Etching is required, so we can see here we have a lot of dots, we can pits here. So these are dislocations. So we can calculate the number per area here, okay, this area. Okay, and let's first talk about slip system for different crystal structures. As we now know that slip system contains a slip direction and slip planes. And here for different crystal structures, we can summarize them. First, let's talk about three basic crystal structure: FCC, BCC, and HCP. And they have different APF. APF is atomic packing factor. Sorry, wait a minute. Atomic packing factor. Okay, and you can see here for FCC and HCP, they have the APF of 0.74. This is the highest one for the APF. And FCC have more slip systems on closed pack planes. So actually, as you can see here, all of the slip systems belongs to the closed pack plane 111. So it will be easy to slip, right? Because more and effective slip system. So the material is ductile. You can see here, we have very common FCC metals: copper, aluminum, nickel, silver, and gold. And for BCC materials, it has an APF of 0.68, a little bit less than that for the FCC and HCP. But you can see here, for this different BCC metals, they have a lot of slip systems. However, none of them belong to the closed pack plane because we only have two closed pack planes. First one is 111 for FCC, and the second is 0001 for HCP. Okay, so for BCC, there is no closed pack planes. We only have its planes with highest planar density. However, we do have the closed pack direction here. So although it has a lot of slip systems, but none of them belongs to closed pack planes. So for the ductility, still good, but it's just not as good as FCC metals. And for HCP materials, it has 0.74. It's very high for APF, but it has less slip systems because although it has 0001, this is the slip plant, However, it just has three sleep systems. Okay, so this one is effective, but it only has three. So it lacks effective sleep systems. So it will make these HCP metals relatively hard to sleep. So the material will become brittle. And also HCP has a lower symmetry compared to cubic. So for FCC and BCC, let's C stands for cubic. And for high FCP metals and sometimes the BCC metals, high temperature is needed for some sleep systems. Okay, and let's talk about the sleep system in FCC structure. So let's first try to find out the highest planar density plane and the highest linear density directions. So they will be 111 family of planes with an octahedral arrangement and also 110 family of directions. A sleep in FCC must occur on 111 octahedral planes because it will have the lowest critical resolve shear stress. This is actually what we mentioned for the closed pack planes and also the closed pack direction. It will exhibit the lowest energy for the dislocation motion. So it will be the lowest tau CRSS. Okay. And then it has uniform distributed 12 sleep systems. So first, let's see which one of the planes is the 111 plane. So this is the meter index, right? 111 planes with intercepts of 1. So this is 111 planes. And then on this plane, we have three highest linear density directions. 1, 2, 3. And for FCC metals, the highest planar density one is the close-packed plane. And this one is also the close-packed directions. And you can see here, we list 12 sleep systems here. And you may wonder, we have a lot of 111 family of plane, right? For example, 111 minus 11, 111 minus 111 minus, and so on. So more than 4, right? And then for 110 family of directions, 110, 101, 011, and then the -1. Okay, also more than 4. Then if this one, for example, maybe 9 times maybe 6, it would be larger than 12. And how come we just have 12 sleep systems? For example, for 111 here, we see 111 with these 3. But we didn't see 111 with this one, right? We didn't see that. This is because the sleep direction must be on the sleep plane. So the normal direction of sleep plane and the sleep directions must be perpendicular to each other. So the inner dot for these two vectors would equals to 0. So we can use this equation to check if this one is the sleep system. For example, 1 plus minus 1, 1 plus minus 1, 1 plus 0 equals to minus 2, not equals to 0. So this one is not the slip system. Okay? And let's talk about more. So we now know that we have 12 slip systems, right? And if we try to increase the external stress to the materials, and then eventually one of the slip systems among the 12 will be initiated. And then after the during the plastic deformations, eventually more than one of the slip system will initiate. Okay, because for the FCC metals, it has a very high ductility. So it must initiate more than one slip system for the plastic deformation. Okay, this is very important. And then the dislocation intersections will occur during plastic deformations. And it means that the slip will occur and the dislocation passing through slip planes. And this dislocation, intersection, or interaction will cause the hardening. And we can see here for these FCC crystals, we have copper, silver, gold, and aluminum. And they have this unique slip system, but it has 12. Detail, we have 12. And for the critical resolved shear stress, you can see here, this value is actually very low. And then let's see the right-hand figure. This one is the stress and strain curve. For the, let's see the A curve, this is the strain hardening, multiple glide. So you see here, with the increasing stress, we have increasing strains. And for this one, first, the strain increased, but the stress increased slowly. It means that it's very easy for this stage, very easy for the plastic deformation. So we call it easy glide. And then after that, it will produce the second stage, strain hardening. And what's the difference between A and B curve? For A, okay, it's equivalent slip system. For B, it's the preferred slip system. So for the preferred slip system, it means that at the beginning, there will be a slip system that is very, very easy for slip. So you see here, it will initiate and land with a very little stress required. However, if all of these slip systems are equivalent, then it will look like this curve. And let's talk about the slip system in HCP. For HCP, we know that it has a closed packed plane, right? 0001, this is also what we call basal planes. It's the closed packed plane, so it will be very easy for the plastic deformation and slip. So for different HCP metals, if they have this slip system, the critical resolved shear stress will be very low. However, because the HCP metals will be different for their crystal structure. For example, for HCP, we know that we have the unit cell edge length C and also A. So for C over A ratios, it will be different for different HCP crystals. And here, for these three, we have low tau CRSS. However, for beryllium, titanium, and zirconium, we'll see that the tau CRSS is very high compared to this one. Okay, compared to this one. And some of it is on the basal plane. However, some of them are not. This one is not the basal plane, but this one is the preferred slip system for titanium. Okay. And let's talk about the C over A ratio. So let's first see the crystal structure of HCP. So you see here, this one with the Z directions, we will use C for the unit cell H length. And here for the A, B, C, okay, you can draw it, for example, like this one. Okay, A, B, okay, not A, B, C, maybe A1, A2, A3. For this three, A1 equals to A2 equals to A3, not equals to C. Okay, so we will have a C over A ratio here. This is a ratio. And then if we assumed the atom is sphere, then we will have a theoretical C over A ratio. This is 0.632. You can see here. For magnesium, it's around 0.624. So it's the ideal, okay, ideal C over A ratio. However, for some of the HCP metals, for example, cadmium and zinc, this one is larger for C over A, and for this three, it's smaller for C over A. And for the ones with equal to ideal or larger than the ideal C over A ratio, you will have low CRSS and have the basal plane slip. Okay, and for the one with smaller C over A ratio, smaller means that the C will be smaller and A will be greater. Okay, so for this one, you have a higher CRSS on basal plane. So basically, for these three, they will have different preferred slip system. And here, because this value is ideal C over A ratio, we assume it, we calculate it by assuming spheres for atoms. But sometimes the atom will be elliptical rather than the spherical. So the C over A ratio will be larger or smaller than 1.632. And let's talk about a special experiment conducted by researchers. So for the tensile stress direction, we usually do this tensile test, right? When the stress direction parallel to the basal plane, so this one. Let's see the definition of phi here. Phi is the normal to the slip plane, this direction, and the angular difference with stress. So when the stress, the tensile stress direction is this one, and parallel to the basal plane, it means that the basal plane is here. And then the normal to the slip plane, the normal, this one, to the slip plane. So these two will be parallel. Okay, so that's the meaning of this one. Oh, I'm sorry, mistake. Okay, let's talk about it again. Tensile stress direction, this one, parallel to the basal plane. We talk about basal plane, not basal plane normal. So the plane will be this one, okay? So this is about parallel to the basal plane. This is the basal plane for 0001. And length, let's see the phi. Definition of phi is the stress direction, this one, between it with normal to the steep plane. So this is the steep plane, then the normal will be this one. So 5 equals to 90 degree. And we take it here. So we will get 0 for tau r. So for these conditions, there would be 0 shear stress on the basal plane. And then, what is the finding of this experiment? So we can find that the slip can still occur on the slip system, and that is not the closed pack plane. So that's what we will see in previous summary. For HCP metals, we have a lot of slip system, right? But only three of them belongs to the basal plane. This is the closed pack plane slip. Okay, so this is important finding for HCP. And also you can see here, this is the summary. We have a special name for this plane in HCP crystal. As we have talked about it for many times, this is the basal plane. Also, we have pyramidal and prismatic plane here. And then let's talk about easy glide. I think we have mentioned it a little bit earlier. Easy glide means that if the slip on basal plane, of course this is for HCP, slip on basal plane can occur. For example, we have this is the tensile stress, right? And we calculate the resolve shear stress, and this resolve shear stress lie on the 0001 slip plane. When this occurred, it can achieve a very large plastic deformations. Okay. However, this is just for single crystal, because for polycrystal materials, you cannot have all of the grain to have these orientations. So for polycrystalline HCP metals, usually it has low ductility compared to the other one. Of course, some of the grains can match this orientation, but I think most of them will not match this 0001. So you will have a low ductility. Okay, it's the PBL question time. And now this is about the temperature effect on slip in HCP metals. And first, the question is, why do HCP metals often need high temperature for plastic deformations? Okay, so the first background you need to know is HCP metals have less effective slip system. For example, you see here, for FCC and BCC, yes, they have a lot of slip systems. But for HCP, you just see here, 3 to 6. And the slip can occur on the slip systems that are not closed pack planes. This is what we learned from the previous slide, right? And now you have these two backgrounds, and please think about it. And let's wait for 5 minutes. Think about it and try to find out the answer of this question based on these two hints. Okay, 5 minutes. Okay, it's about time. Let's talk about the answer of these questions. So, as we said, for FCC and BCC metals, because they have a lot of sleep systems, although BCC metals, they are not that effective. So, the second sleep system will eventually initiate, besides the most favorable one. However, for HCP metals, if the external stress directions is for these two conditions perpendicular to the most favorable oriented sleep direction, this one, or this one. So first, let's see the definition of these two. This one, first, if lambda equals to 90 degree, it means that the external stress direction, for example, this one, is perpendicular to the sleep direction, perpendicular, 90 degree. Okay, so you cannot have any resolved shear stress from this line to this lines. So no resolved shear stress. And then the second example is phi equals to lambda 90 degrees. So when external stress direction, this one, parallel to the sleep plane, for example, this plane here. Okay, then this condition, this stress will be on the sleep plane, but this one is pure tensile, not shear. So we have a lot of stress, but it belongs to tensile stress. So again, zero stress here. So for these two conditions, there will be 0 tau r here. And it will cause the fracture. Fracture will occur due to zero resolved shear stress. And less wide, for example, we have only three sleep systems, and one of it could match this condition or this condition, but we still have the other two. And why we need to increase the temperature? This is because for these two conditions, the Shimi factor, these terms, could be very low. If this factor is very low, then it will be hard to sleep. But in FCC and BCC metals, they have 12 to 24 sleep systems. So there is a very high probability for that to have a very high Shimi factor one, so that it will be easy to sleep. Okay, so the answer to this one, the temperature effect, why we need to increase the temperature, why we often increase temperature for sleep in HCP, because HCP metals have less effective sleep system. Okay, this is the answer. And then let's talk about the sleep system in BCC. Okay, for BCC, it has a smaller IPF, and also there is no close pack plane for this one, but it has a close pack directions. And the most close pack plane is 110 here. And it will cause a consequence of less effective sleep system, less. So regarding the effect, is less effective, but the number is very high. Okay, so you will have a higher CRSS than FCC. Okay.